In this video, we're going to look at solving logarithmic equations using the log properties. Now, if you don't remember what those log properties were, there are three of them that we discussed: the product property, the quotient property, and the power property. So let's take a look at our first equation and see how these properties can be useful in helping us solve. So looking at my first equation, I have three separate logarithms. Now, how am I going to get rid of these logs? Well, the answer is I'll eventually apply inverses or use the one-to-one property. Now, in this particular case, I'm going to need to combine the two logarithms on my left-hand side, and I'll do that using the quotient property. So what happens if I use this quotient property is I can turn this subtraction of two logs into the log of a single value, which is my first value, 3x, divided by my second value, 6, is equal to the log of 5. Now, from here, I can apply the one-to-one property because the two logarithms share the same base. Therefore, the internal parts of those logarithms would have to be the same. So I'll end up with the left-hand side, or what's inside the log of the left-hand side, which is 3x over 6, which you may notice actually reduces to x over 2, is equal to the left-hand side, which is 5. So I end up with the value for x is 10 when I multiply both sides by the least common denominator. Here are two other examples. Now in the first one, I'm going to go ahead and use the product property to combine these two logarithms, just like before, into a single log base 3 of the product of these two things. Well, the product of 2x plus 3 and x will give me 2x squared plus 3x is equal to 2. Now that I've isolated the logarithm, instead of having two logs, I now have one. I can go ahead and apply the inverse of both sides, or the inverse to both sides, to get this logarithm to cancel out. So I'm going to exponentiate by 3, raising both the left and right-hand side as the exponent with a base of 3. So because exponentials and logarithms are inverses, these two are going to annihilate each other and leave me with 2x squared plus 3x. And on the right-hand side, I have 3 to the second power, which is just 9. Okay, so I'll go ahead and bring that 9 over to the left by subtracting it from both sides. And I end up with a quadratic equation in standard form. So now that I have a quadratic equation in standard form, I could go ahead and solve by any of those methods that we have discussed to solve quadratics. This one, in fact, factors to 2x minus 3 times x plus 3, which tells me that either 2x minus 3 equals 0, or that x plus 3 equals 0, which occurs when x is 3/2, or negative 3. So I get two solutions, 3/2 and negative 3. The only problem is when I plug negative 3 in to my second logarithm, I'm taking the log of a negative number. And because the domain of all logarithms is from 0 to infinity, negative 3 is not part of that domain. I will not be able to plug it into the second log. Therefore, I'm going to reject this as a possible answer. And I end up with only one solution, which is x is 3/2. In the last one, in this case, I have a natural log, which remember is a log base e. So again, before I can get rid of these natural logs, I'm going to have to convert them into a single logarithm using log properties. The single logarithm using the quotient property will be that of the first value, 10, divided by the second value, x plus 9, is equal to 1. Then to cancel out this logarithm, I'm going to apply inverses of both sides and exponentiate by the base, which is e. When I do that, these two values will cancel out, leaving me with 10 over x plus 9 is equal to e to the first, which is just e. Now I have to isolate x, so I'm going to multiply both sides by x plus 9 to get these denominators to cancel out. So that I'm left with 10 is equal to, and now I'll distribute that e, and I get e times x plus 9 times e. And then to isolate x, I'll subtract 9e from both sides, and then divide both sides by e. So that my final answer is x is equal to 10 minus 9e divided by e. Okay,